Hey, it works. That's a good sign. I'm always a little bit nervous getting different programs to talk to each other on a new desktop machine. That's always a little bit sketchy the first time. Well, it looks like it's official. We can get started, folks. So we're about to finish off our midterm week, and really the only thing we have on our list right here is section 3.5. We may take extra time to finish this section, so no guarantee we finish it today, but we'll take extra care with that one. I feel like after doing the product rule and quotient rule, those aren't too bad with enough practice. But the chain rule is probably the more tricky differentiation formula that we're going to see on these notes. So we'll go very carefully, methodically to really see how it all goes together. And as far as the rest of the announcements, quiz number 4 is due today, and we have our 5th quiz posted. This one will be due next Wednesday. And next Wednesday is also our 3rd exam. Any questions at all, folks, so far? Okay, oh, I did forget to mention, I think I said it once, but that was before class started officially. We're using a whole new system now, a desktop system. So hopefully the desktop doesn't get hot and then things like Wi-Fi get spotty. I'm not too sure if that was the problem, but we'll see if this corrects that issue we had last class. Also, it's a new camera system. This is the OWL camera, which is a really weird setup. I've got the camera over here and I've got the monitor over here. So you're probably going to see a lot of just the side view of me. By the way, my head is a little flat, not because of weird cranial surgery, more because of just wearing headphones all day. So you get to see that as well. And for the other announcements, moving down further, we mentioned this last time, but this is our second exam. It's going to be next Wednesday, October 16th. Yep, that would be the 16th for sure. It's going to cover from continuity, section 2.5, up to the differentiation rules, section 3.3. So we're not getting into product rule, quotient rule, nor the chain rule on the second exam. Same rules on the exam. It's closed book, closed notes, but you're welcome to have a calculator. As long as it's not a non-graphing calculator, these are the two main options. You'll be all set. So I think that's finally our full set of announcements. Any questions or comments whatsoever, folks, before we jump into section 3.5? Okay, let's see what the chain rule is all about. Again, this is a new desktop, so it's going to take me a moment to just get acclimated to actually using this thing. One thing that's kind of nice about this desktop is Microsoft Word is way, way out of date. Somehow this program didn't get updated on this workstation. And if you're familiar with Microsoft Word, the old versions are nice because you can load a whole bunch of different pens, as many as you want. I couldn't do that on the last system. That's why I was always switching pens constantly. So that's, a bit of a nice feature there. But aside from all the newness and oddities here, let's get started. So with the chain rule, oh, I got a little thing there. The idea with the chain rule is that it's a formula where things get multiplied together. So example 1 is kind of a silly example, but it's just a good way to get started thinking about the chain rule. So here's how it goes. It starts off by saying a car goes twice as fast as a person on a bike. Imagine we're in a school zone and person on the bike is going rather rapid, maybe. But if they say here, twice as fast, fast is referring to a rate of speed. And so now we're dealing with a derivative. So this whole sentence, a car goes twice as fast as a person on a bike, can be represented this way. The rate of speed of the car with respect to the bike is 2, for 2 times as fast. Any questions, folks, with that first sentence? Still trying to get used to looking over here to ask a question and looking back over here to see if there are questions. It's going to be a little bit weird, but we'll get used to it. So same idea with sentence 2. It says a person on a bike goes 3 times as fast as a person on foot. Writing that out as a derivative in Leibniz notation would be the rate of change of the speed of the bike with respect to the speed of the person on foot is 3. To say the person's going 3 times as fast. So now a lot of people can guess this answer to this question pretty quickly. Here's a rundown. For comparing a car to a bike, car goes twice as fast. Comparing a bike to a person on foot, well, the person on bike goes 3 times as fast. So now the larger question is, how much faster is the person in the car than the person on foot? It's kind of a wild question because it's relating that derivative to that one. Wow, that's kind of wild. Let's tone that pen down. Anyone have a good guess for what that value should be? Oh, we got one in the chat. I agree with Eli. You're absolutely correct. It's 6 times as fast. Thinking about it, if the person in the car is twice as fast as the person on the bike, person on the bike is 3 times as fast as the person on foot, then the person in the car must be going 2 times 3, so 6 times as fast as the person on foot. Thanks for that response there, Eli. Really, the whole purpose of example 1 is to show our formula for the chain rule seems plausible. It should be a multiplication formula, because in this context already, it just makes sense to multiply. In fact, 6 times as fast is the right answer down here. But here's how we would actually write this out if we're using this notation. We would start by saying the derivative for car with respect to the person on foot. We break it down first in this way. It's going to be equal to the rate of change for the person in the car with respect to the person on the bike. So we're using this derivative right here to throw it in. Then we multiply by this derivative, the rate of change with respect to of the bike with respect to the person being on foot would now go together in this way. But notice once you write these two things down, it's nothing but 2 multiplying 3 for all rate of speed as of 6 times as fast. Again, this is one that's not too bad to guess, but writing it down like this is the weird part. Well, at least it's important to remember that this right here is just a derivative in Leibniz notation, so it's not a true fraction. But if you thought of it as a fraction, just as an analogy, it kind of makes sense because with fractions, you cancel this way, and you recover d car divided by d foot, the thing on the left. So this is essentially the chain rule right here in Leibniz notation. And again, the major punchline is the chain rule is a type of multiplication formula. In many, many contexts, even in this simple example here, rates of speeds just multiply together. The chain rule makes this a little bit more general and shows when you calculate derivatives, when you do get a multiplication formula just like that one. So that's what we're going to be exploring in great detail on these notes. Any questions at the moment, folks, with our initial example? Okay, well, let's take a look at next page here. This is the formal definition of the chain rule, and we'll take some time unwinding this. This is our major goal, is to understand this formula right here. So let's begin at the top. It begins by saying, if g is differentiable at x, and f is differentiable at g of x, then the composite function, defined in this way, f equals f of g, is the way we indicate a function composite. It's also defined by f of x equals f of g of x. So this f of g here is just a symbol And that's the actual thing you would be calculating when f of g comes up. Starts to make sense how this is going together then. We wanted g to be differentiable at x, so we plug that in. And we want f to be differentiable at g of x. So there's the f function. It's differentiable at its input, g of x. So this function f of x is differentiable at x, and the derivative f prime is given as this down below. Let's undo the color coding just a bit so we can focus on this new thing. If we want to calculate the derivative of that f of x right up here, what we do is we first differentiate f. There it is, f has been differentiated. We input inside f the function g, but the function g right here is totally unchanged. It just copies in, and then we multiply by the derivative g prime at x. So that's the multiplication part that we were hinting at on the prior example. There's a great way to organize this kind of stuff that we use a lot, just to see how it all comes together. The function f, I'll often put a 1 here to say we differentiate it first when we use the chain rule, not the train rule, the chain rule, and we call this the outer function. It's outer because, well, the function g of x goes inside f in this function composition. So f is the outer function, and g is the inner function. So again, I'll always do this when we're organizing a chain rule to study how it comes together. 1 here just says, the first thing you actually do is this. Step 1, differentiate f, and then step 2, differentiate g of x. Multiply the results together, and you've got the chain rule set up. So just like the product rule, quotient rule, and now the chain rule, this is one of those formulas where it's a very powerful technique. This is a context on the left where we should never use the chain rule. And this is a context on the right where we absolutely need to use the chain rule. There's no other way to differentiate this thing. Well, any questions, folks, about the setup of the formula before we try it out? Okay, so next thing to do on this, let's do this one right here where the chain rule is required, and then we'll show how on this problem, we absolutely didn't need it. So if we're going to differentiate that function, first problem we have is, well, we don't like the square root symbol so much in calculus because it makes the power rule a little bit foggy, how it's actually being used. So step 1, do a little bit of a correction on that thing and take the radical notation, the fact that that's a square root, and write it as x plus 1 to the power of 1/2. Now we're ready to go. There's really 2 functions in here. Again, you're using the chain rule whenever you have a function composition. Visualizing it this way is probably a little bit better, f of g of x. When you see that, the g of x function right here is the function that's on the inside. So it would be the x plus 1 in this case. The f of x function, the outer function, is going to be the power 1/2. So let's start organizing like we mentioned. This is the first derivative we have to calculate, so I'll label it as 1, do that derivative first, and that's the outer function. Derivative 2, the inner function, is this one, and oftentimes it's a little bit easier to spot the inner function because it's literally something inside some other function. So that's our initial analysis. Essentially what we're doing is we're thinking of a composition like this one, but we're focusing more on each component part, what the inner function is, what the outer function is. Any questions at all, folks, with that analysis here? Okay, well, let's finally differentiate this thing. The way we differentiate this looks a little bit odd the very first time you really get going with it, but it's truly just this format. So I'll keep an eye on this as well as we go to do the steps. Starts off as y, so now we're doing the derivative, y prime. We first differentiate the outer function. It's a power 1/2 function, so we're just using the ordinary power rule. In the power rule, that 1/2 comes down, there it is, And you absolutely want to leave just a placeholder here. That's kind of a strategy we've been using quite a while. Leave one big placeholder, and now put the new power where the red dot is. We're always subtracting one when we differentiate. So this is subtracting 2 over 2, and we get a negative 1/2. So that's taking care of derivative 1, the outer one. Notice I still haven't plugged anything inside here, but that's probably a good pattern for the chain rule. Focus on doing the outer derivative, leave a placeholder where the input would go, and immediately right after, indicate this step. The way we do it on paper is we go times some derivative. Don't forget that prime symbol here to indicate we're multiplying by new derivative, which is indicated here. So next step, and this is a tricky step. Notice right here by the red dot, g of x just goes right inside the derivative. There's no prime symbol on that g of x, so it's directly copied in. On a real example like this one, x plus 1 is the inner function, think of the g of x. It copies directly inside here, left totally unchanged. So there it is, x plus 1. That lines up with this step where g of x goes in. Next, you multiply by the derivative of g of x. So this x plus 1 also copies right here. And on this one, when we said derivative 2 is the inner function, that's exactly what we're doing right there by the red dot. The inner function is x plus 1, and we're differentiating it. Well, just about there with that one. All we need to next do is finalize that last derivative. Any questions or comments so far to this stage? Okay, well, turns out this derivative wasn't too spectacular on its own. The derivative of x is 1, derivative of the constant is 0, so that whole derivative here is just a times 1. So we can say, if we like, the derivative is 1/2 x plus 1 to the power negative 1/2. And our work is done right at that step. So that's how the chain rule goes. Our whole goal in these notes is just to practice that technique over and over again. Next, we'll try out this one, where we should never use the chain rule in this context. Not because we can't, not because we get the wrong answer. We can use the chain rule and get the right answer on this thing, but it's the same kind of issue we've had in the past. This function here is so fast to differentiate that doing the chain rule is just increasing our odds of making a simple mistake because we're adding a whole bunch of unnecessary steps to the process. Before we try this one out, any questions about the last one? Okay, so what makes this one not a chain rule problem is, well, we're going to do the same thing as what we did over here, but there's only one term inside the square root symbol, just x cubed. That means when we go to write this as x cubed to the power of 1/2, we can actually work with that power of 1/2. It was impossible here, and it's because of the two terms. You can't take x to the power of 1/2 plus 1 to the power of 1/2. That's impossible algebraically. But over here, in this configuration, exponents will multiply. So we get that this is x to the power 3 here times 1/2 just gives us 3/2. And differentiating this, that's just an application of the power rule directly. So pretty much done with that one. We can say y prime is 3/2 x to the power of 1 less, so subtract 2 over 2, and we get 1/2 on that answer there. We did it, folks. This is the case where if you just do something algebraically, oftentimes you can eliminate the need for a chain rule. And this is a case where nothing algebraically can help us whatsoever. We just have to use the chain rule. Any questions or comments on either of those problems?
Why did you put x to the 1/2 again? At
This one right here?
Yeah.
Oh, gotcha. When we went to take the derivative, we have to subtract 1 from that power. So we went 3/2 minus 1, but that's just the same as 3/2 minus 2 over 2. And so we got a power of 1/2 altogether coming in right there.
Perfect. Thank you.
Yeah, absolutely. Other questions at the moment? Whoa, still don't know how I end up bringing that up. Okay, well, let's try out another chain rule problem just to see how all this goes together. We're still in the process of just understanding what that formula is trying to say. And this is one of those weird examples where we don't have the actual functions, just some collected information about each function, and we're going to evaluate f prime at 0. The whole purpose to a problem like this one is, once again, just to look at the formula a little bit further to try to understand it better. So these are not very typical kinds of questions, but they sometimes do come up on homework sets, potentially a quiz problem as well. So here's the restatement of the whole chain rule once again. We have a brand new function. F of x is the composition of f times g of x, and we want to evaluate f prime at 0. We know f prime of x goes this way. The formula is supplied just right there. We're looking at it. So if we want to do f prime at 0, all we're going to do is use the original formula and put 0 everywhere x occurs. So let's start by just writing out the formula. F prime evaluated at 0 is going to be lowercase f prime at g of 0 multiplied by g prime at 0. So that's our setup so far. Really, all we did again is put in zeros here because we're evaluating f prime at 0. Next, we have a whole bunch of information here about the function or its derivative. But what makes this problem a little bit trickier is some pieces of this information actually doesn't help us. Other pieces do. So we have to find the right values to use here. We won't actually be using all of them. But let's say g prime of 0 is a good place to start. G prime of 0 gives us a value of 4, so we can plug that in. We also have g of 0. And g of 0 is an 8. So let's start by just plugging in those two pieces of information. So on our next line, f prime of 0 is now equal to f prime evaluated at g of 0. Already forgot what that was. Looks like it's an 8. So that's our first substitution. Then we're multiplying by g prime at 0. G prime at 0 comes out as a 4, so it's just times 4 at this stage. So after doing that, we just take a look. We have f prime of 8. F prime of 8 does give us a value right here at -2. Let's just slap this with a huge color coding marker once again. So -2 goes here. It's going to kind of overwrite our highlighting, but that's all right. So this whole thing, f prime of 8, we'll throw in a value of -2. So next line, we have -2 times +4. So in total, f prime of 0 becomes -8, unless I messed up my arithmetic somewhere or misdone a substitution. So it looks like the only thing that was a trick on this problem was the f of 0 equals 3 is totally irrelevant to the whole problem. Well, again, that's how the derivative goes together. Any questions at all, folks, with this kind of a wonky example, in all honesty? Okay, again, this is just our third look at what the chain rule is, how to work with it. The problems that we'll be doing next are probably about what you would expect. For example, 3, we're just going to start using the chain rule over and over again. But you know what? We're still learning that thing, so let's carry this down just to the next page. It will be available when we do it for the first problem, at least. Then after we do some derivatives like this, getting some good practice in, we have next an extra interesting formula for calculating the derivative of an exponential function here. Notice we only have one derivative along these lines, which was if y equals e to the x, then y prime is the same, e to the x. But if you have a different base, this formula is now going to extend on that. The reason it appears here in section 3.5 is you actually need the chain rule to show that that formula is true. So we'll see how those formulas work. And finally, we'll end on just one of these kinds of applications once again, like we've seen before. Looks like this one is coming from biology. So before we get to all that, let's just start off right here, getting more comfortable with the chain rule. So it says calculate the derivative, simplify answers. And looking at this thing, we have a degree 3 polynomial being raised to the power of 103. So kind of a ridiculous problem, but it's still just an ordinary standard chain rule type of problem. The inner function on this one is where it's the 8x cubed plus 9x squared minus 11x plus 6. So the power 103 is a power function. We have to do that one first, and that is the outer. The inner function is this one. The whole thing, degree 3 polynomial that we have inside. Any questions with the outer function, inner function analysis at the moment? Okay, I think this works pretty well with color coding. So let's think of the outer function as being the one in blue. Inner function is the one in green. And it starts off this way. We're just differentiating it directly, and f prime of x is going to be first. We do this part. We take the derivative of f, the outer function. So we'll get, in our problem, 103 comes down as a coefficient. Something goes inside those parentheses, but we want to finish out the whole derivative and drop the exponent by 1. So 103 turns into a power 102. Next, we multiply by the derivative of something. That's this part of the formula. So we immediately say times the derivative of something. So this finishes out part 1 and gets it set up for part 2, differentiating the inner function. Now, next step we take here is whatever the inner function is, notice from right here, it copies in just as it is. This is sometimes the confusing step because we want to differentiate a whole bunch of stuff. But we have to resist the urge on this one when we copy it down here. That's the g of x right here. And so it's going to be 8x cubed plus 9x squared minus 11x plus 6. So it directly copies in here. We're multiplying by a derivative of the same function. So when it copies down to the next placeholders, we differentiate it on the next step. So 8x cubed plus 9x squared minus 11x plus 6. So that's our first step of the chain rule. When people get really fluent on doing this, I'll assume that you've probably done the chain rule 30, 40 times. A lot of times people just place the derivative right where that is, saving a step. But when you're learning the chain rule, I highly encourage you to take the 2 steps that we're taking, the 1 additional step, because it really helps to see how things are coming together without getting overwhelmed with tons of steps in one line. Any questions, folks, so far to this step? Okay, next thing we do is, that's a lot of copying. We start by saying, copy up to this point right here where the red dot is. So far, f prime of x is equal to 103, 8x cubed plus 9x squared minus 11x plus 6 to the power of 102. This is in black just to say we're copying things. I'll maintain the color coding if we ever take a derivative. So that'll be a pattern I try to maintain through the notes. Differentiating this thing right here is just back to section 3.3. It's a degree 3 polynomial, so it starts with 3 multiplying the 8. Get 24x squared. Over here, 2 multiplies 9 to give 18. X to the power 1, so we'll just write x. That term turns into a negative 11. And now we're done. The constant 6 goes to 0 in the derivative. So this is the result, the whole derivative by using the chain rule. We did it, folks. I'd say that's the first really official problem that you'd see in the homework setting, stuff like these here. Any questions or comments whatsoever getting through that first one?
Is that like the answer, the final answer? We don't have to keep going after
Yes,
that?
absolutely. There's no other additional steps you'd have to take with this. So I would just type it in directly like that as an answer. Any other questions with that one? Okay, again, it's a big answer. It was a kind of a big mess of a function to start this one out, but it's kind of impressive because you could really do this in two ways. If you had the time and the patience and lots of paper, you could just FOIL this out with the power 103, get a polynomial with many different terms, and just differentiates term by term by term. Or this is just as equivalent as an answer, and it's equally good. So for our part B coming in next, this one has the same kind of challenge that we've been dealing before. In fact, this is the same sort of challenge in quiz 4 with some of the things we're differentiating. If our variable x is in a denominator, well, we can't use the power rule whatsoever on that thing. And even worse, there's a radical sign. This is the fifth root of something. So we want to correct two things on this function even before we think about differentiating. We'll start by saying that given function is equal to 9 divided by, where it's a fifth root from right here, that converts into an exponent of 1/5. So it's now just 2x squared minus x power 1/5. So our first requirement is taken care of. We have the actual exponent. We need that if we're using a power rule. Second problem is our base with the exponent shouldn't be in the denominator. That makes everything way too complicated. We don't want to use a quotient rule if your numerator is a constant. That's way too many additional steps. So we take this, use another exponent law that says we want that in the numerator. It's totally doable. We'll write it in as 9, 2x squared minus x. The only thing you had to do with the exponent is change its sign. So it's now a power of negative 1/5. So at that stage, again, we have done zero calculus to that thing, but it's ready to go with differentiating in this format. Next step, we're going to say f prime of x equals something, but we want to do our initial analysis like before. You might start to see a real pattern to these kinds of things. If you have an outer power like the 103 there, or the negative 1/5 on this one, that is definitely going to be your outer function in these kinds of problems. So negative 1/5, that's derivative 1 we'll take care of, outer. Derivative 2, the inner function. Again, this one is usually always easiest to spot because it's inside the other one. So that's going to be our analysis. Following this pattern once again, it's going to start off like this. Let's use some color coding as before. So there's the outer function. It's a power negative 1/5 function. Inner function is the degree 2 quadratic. But since we're doing this first, we'll take the 9. It's left unaffected by the constant multiple rule. This 9 will be multiplied by the negative 1/5. Then we throw in a parenthesis, put in the new power. We're subtracting 5/5 on this one. So if your denominator is 5, you're really just subtracting 5 from that numerator. That was a great way to think about that one. So it's going to be negative 6/5. In the chain rule, we're always multiplying by the next derivative. That's this part right here up above in the formula. So times the derivative of something. Now we have two open parentheses, so two placeholders. This quantity, the inner function, always copies in both of them at once. Again, this is a really effective strategy for learning it because it's sometimes really foggy with our mind on where everything connects in. But if you put in the placeholders first, it gives a lot of direction. So we know now at this stage, 2x squared minus x goes here and here. The only last thing to do here is just multiply this derivative out. And like on the last problem, we'll have our total answer. Any questions at all, folks, to this stage of the work? Okay, well, let's finalize this one. We need to multiply our constants together, so that turns into -9/5. You don't have to do anything to these exponents, so we can just leave it as a negative exponent, and that's always totally fine in this class. So 2x squared minus x to the power of -6/5. And here, we still have to crank out that last derivative, but it'll become a 4x minus 1. The 4x came from multiplying the 2 by 2 here, dropping the power by 1. And whatever you see at x, that's either going to be a 1 or a -1, according to whatever the coefficient is right in front. So finally, we got it, folks. The chain rule gives us that mess. But at least we can now differentiate a huge extra category of functions, because these are things we could have never have seen in section 3.3, 3.4. So with the chain rule on the table, more and more things can now be differentiated. Any questions or comments at all, folks, to that stage? Okay, well, let's keep on going then. So far, we've done some pretty routine kind of examples, but not all the examples are this contained. Sometimes the work does get a little bit more spread out, and I think that's what we're going to deal with on part C here. And part D. I think actually part D is a little bit faster. So there's a couple questions in the actual homework where some of the work gets just a little bit more spread out. And these are the last two questions on the notes where it's meant to support those problems and the WebAssign homework. Looking at the setup so far, the struggle with this problem is not the chain rule, actually. Doing the chain rule on either this piece by the red dot or this piece by the red dot, those are not so bad. Those are essentially part A of this on these notes for this example. What makes this one hard is it's a product rule at the same time. And getting out of the product rule isn't easy because you'd have to raise this to the 4th power. That's doable, it just takes a long time. Raising that one to the 8th power is less doable. This would take way too much time. I don't think I'm accurate enough to get that done. I'd be too stressed out writing really fast. Our hands would get tired. So this one is best to just analyze purely by product rule to start. So I'll keep the color coding relative to the chain rule, and let's just carefully begin by saying this. This one requires the product rule. So set up to the product rule goes like this. G prime at V equals derivative of the first function, copy the second function, then do it all over again, except this time on the next term, copy the first function, differentiate the second function. So here's the product rule all set up for us, 4 placeholders. 2v squared minus 7 to the 4th power goes into the first positions, the first placeholders. So 2v squared minus 7 to the 4th power goes here. And here. Next, we take this, drop it into the last positions. So v cubed plus 5v minus 1 to the 8th power goes here, as well as over here where it's differentiated. So v cubed plus 5v minus 1 to the 8th power. So it's a lot of writing, but we're definitely getting there. Imagine this one is kind of like 2 problems duct taped together through the product rule is essentially what's going on. Any questions or comments with the first step with product rule? Okay, well, as before, we have 2 derivatives. This one here is still a chain rule, as well as the one on the very end. So let's carefully maneuver through those. The power 4 function is going to be the outer on that first one. The power 8 function on the second one is the outer function. The inner functions on both of those are the things inside. So 2v squared minus 7, that would be derivative 2, the inner. And likewise, v cubed plus 5v minus 1 is derivative 2, the inner as well. So that's our setup. All we need to now do is very methodically crank out those derivatives and copy every single thing that follows right after. Again, what I think makes these problems kind of hard is that there's just so much stuff. It's easy to make a mistake by not copying something, for example. So doing this methodically, we'll say it's equal to derivative of the outer function, we'll place a 4 in front. New power is 3. And then we multiply by the derivative of the inner function. We're going to have to copy this in next, so let's just copy it in so we don't forget it. It is b cubed plus 5b minus 1. Next thing we do in this chain rule setup is drop 2v squared minus 7 here in open parenthesis, and in the next open parenthesis as well. So 2v squared minus 7 into this one at the same time. So that took care of that chain rule. We copied that function just so we don't forget. Now a little bit more copying up to this stage, plus 2v squared minus 7 to the 4th power. After doing that copying, we now do this chain rule over here. Same strategy, just in a different place. Differentiate that function, and first 8 comes down. So here's times 8. The new power is 7. And next we multiply by the derivative of what's inside. So here's what our setup looks like. Our inner function goes into both of those open containers. So here, b cubed plus 5b minus 1, and here. So we're almost there, folks. Just 2 more derivatives to take care of, and those are ordinary derivatives. No chain rules on either one of them. And we'll have our answer. Any questions or comments on how this all came together?
With the black terms in the middle, why is it not to the 8th still?
Oh, that was the mistake I was mentioning quite a bit. I actually fell a victim to it. That power 8 you see right there should have been copied down. That was my mistake. Thanks for spotting that as well, Emily. So 8 to 8 right here. Let's highlight that in yellow for that omission. Again, that's one of the things that's a real danger in these kinds of problems. So much stuff means even if a chance of a copy error is really small, if you have to copy a lot of stuff, there is a good chance of it actually occurring. Other questions or corrections so far, folks, to this stage? Okay, once again, thanks for spotting that 8 there, the missing power from the original one. And the next steps we'll take is loads of copying up to this spot. Let me actually put my equality to the left so we can fit it all. It's 4 2v squared minus 7 to the 3rd power. Then over here, we differentiate this function in green. We'll start by taking 2 times 2 for a 4v minus 0. So altogether, this is just a 4v. Then it multiplies up to here, multiplies this function here, v cubed, plus 5v minus 1 to the 8th power, plus 2v squared minus 7 to the 4th power. More terms coming in. We're copying all the way to this spot, so times 8. v cubed plus 5v minus 1 to the 7th power. And now we're doing the last derivative, this one here. When term by term, we start with 3v squared plus 5 from the second term here, and then plus a 0. So it looks like we have everything in our line here, unless anything might have been miscopied or just is missing. Last steps we're going to take is just multiply 4 by 4, maybe move the constant 8 in front, but nothing too major. This is essentially the answer right at this stage. We're just trying to clean it up a little bit. Any questions whatsoever, folks, to this step? Okay, well, let's come over here and just start copying things in. Again, I'm going to move the 4v to the very front, so it's going to turn into 16v. So start with 16v, 2v squared minus 7 cubed, v cubed plus 5v minus 1 to the 8th power plus Here, all I'm gonna do is move the coefficient 8 in front, not because it's required, but more, this is a stylistic choice that I personally would always make. I do think it makes reading the next line a little bit clearer, because now we know we have a constant 8 to start. 2b squared minus 7 to the 4th power, multiplying v cubed plus 5v minus 1 to the 7th power, multiplying 3v squared plus 5. Kind of an impressive mess. You could do even more to this. You could factor out the greatest common factor. I would say this is a good stopping point unless you were doing something additional to this problem. If you were solving an equation relative to this derivative, you probably would want to factor. But if all we want to do is calculate a derivative g prime of v, I'd say this is a pretty good stopping point. Well, we did it, folks. I think this is going to be like the hardest problem of the whole day. Any questions about how we maneuvered through it? Okay, well, let's try out just another one kind of along these lines. Really, the purpose of part C is just another reminder we thought about in the last section. The reminder is every single time we pick up a new formula for differentiation, it interacts with the prior formulas. So these are all really interconnected. The chain rule doesn't exist in isolation, nor does the product rule, quotient rule, constant multiple rule, and on and on. You can write down a problem where you use every single differentiation formula that we've talked about in class so far. That would be a kind of out of the line type of problem. But these ones are not too atypical. We'll encounter stuff like this quite a bit in the applied sections. So let's take a look next. Do one more along those lines. Part D is also a chain rule problem. The outer function is the power 6. The inner function is the fraction that we see here. But when we go to differentiate that fraction, we are also using the quotient rule. So let's say for this one, this requires chain rule, then the quotient rule. So let's start by doing the typical setup we would for this kind of problem. The outer function is the function that takes something and raises it to power 6. So we have to handle that derivative first. That one's the outer. The inner function, again, is usually easiest to spot. It's the thing inside something. It's this rational function here. So that's function 2. Inner, or its derivative 2, the second derivative we'll take in the process, and we'll differentiate that one first. So all this analysis, we begin by writing h prime of t equals, I forgot the input variable, h prime let me move that cursor out of there. H prime of t will first be equal to, going down the line, differentiate the outer function. It's a power 6 function, so 6 copies down. And the new power must be 5. Then the next step you always take in the chain rule is you multiply by a new derivative. The derivative you're taking is that one right there. So it copies in 2 positions. First here, t squared minus 3, divide by t squared plus 3, and then over here, t squared minus 3 divided by t squared plus 3. So in the middle of this problem, we have to do a quotient rule, and that means there's a lot of strategies for doing this one. We can just copy everything and move line by line, trailing off with equalities. I think a better approach is just do this derivative right here, and then plug it back in for h prime of t. So let's go with that route. Any questions first to this stage? Okay, so we're making a slight detour by calculating t squared minus 3, t squared plus 3, prime. This one's a quotient rule, so let's be careful with the setup on this one. A quotient rule starts off kind of like a product rule. We differentiate something, copy the opposite thing. Here's the first change, we put a minus in. copy the top function, multiply by the derivative of the bottom function. And the next change is we square the bottom function. So here's our setup. This time it has 5 placeholders, but still I think the chain rule is more challenging of a process, even though this looks more impressive. The top function, t squared plus 3, is going to go here and here. So t squared minus 3. And there. Finally, the bottom function goes in all of the remaining positions. So it copies in here. Over here where it's differentiated. And down below where it's simply just going to be squared. So here's what the quotient rule looks like on that thing. And that's why it's sometimes not a bad strategy to separate out a piece of the problem if you suspect it's on its own, like a whole problem, a lot of writing. Any questions to this stage of the quotient rule setup? Okay, well, the derivative goes pretty fast once we get to this stage. By where the red dot is, that derivative is just a 2t. It's multiplying t squared plus 3, subtract t squared minus 3. This derivative turns into 2t again, so times 2t. All of which is divided by t squared plus 3 squared. Next step we take is we need to simplify this function. So 2t is going to multiply here to give us 2t cubed. And here to get plus 6t. On the next distribution, we're really distributing 2 things at once. The negative distributes this way, so it's a negative t squared. 2t distributes this way, so it's a negative 2t cubed altogether. Or another way to visualize it, think of this as just being a negative 2t multiplying the t squared for a negative 2t cubed. Then we just redo that. Let me retune these arrows. Negative is going to multiply this, so now it's a positive 3. 2t also multiplies, so now it's a 6t positive. So plus 6t. And that prior exponent looks a little bit off. Let me fix that one. So we've done our distributions. The denominator is still t squared plus 3 squared. And now we have cancellations to boot. So we have 2t cubed minus 2t cubed. The whole thing just turns into 12t divided by t squared plus 3 squared. So that's this quotient rule portion of this function right here. I don't want to scroll too far, so hopefully we can keep the whole problem on one page. Any questions or comments, folks, on getting that quotient rule to finalize? Okay, so our last step on this one is we take all of this, that product right there, which came from the chain rule, we're plugging in just that. So we can now say h prime of t at this stage is equal to, well, this actually simplifies more than we'd expect. So let's do a little bit of exponent work on this thing. 6 is going to stay in a numerator. When you raise a fraction to a power, you can raise the numerator and denominator individually to that power. So this can be 6 times t squared minus 3 to the 5th power, divided by t squared plus 3 to the 5th power. So all I've done is broken up this fraction by raising the top and bottom to power 5 and multiplied the numerator by 6 in this way. Then from over here, we make a substitution and say it's times 12t divided by t squared plus 3 to the power 2. Let's put that in yellow, not scribble on it. Let's put that in yellow just to say where the substitution came from. And here's finally the extra simplification that does happen on this one. We can take the 6 multiplied the 12t to get 72t. Let me try the hell over again. There we go, 72t. Then it's multiplied by t squared minus 3 to the 5th power. But now in the denominator, we have t squared plus 3, t squared plus 3 again. So these are like bases, and the exponents 5 and 2 would add up. So we have down below t squared plus 3 to the power 7. So finally, hey, we did get it in one little screen page. We don't have to scroll to see the whole thing. That's our total answer to the derivative of h of t up here. Just another random function. I guess h is because it's kind of a harder problem compared to the rest. If you break up the problem into little pieces, like how we differentiate this as a quotient rule all on its own, it makes it all a little bit more manageable to get through. The problem before, this one, it was kind of harder to break it up into pieces, so we just did everything on one line by another huge line and going and so on. Well, any last questions, folks, on getting through part D? Okay, well, we're nearly through the notes. We have about 20 minutes and some change. Oh, we do have a question. Drop to power. Oh, let me take a look. Was it at the last line? I'm not too sure I'm seeing where the power could have gotten dropped. Anyone else see where it might have been? Oh, gotcha. Well, I think I opened up my chat and just saw a different message. Sorry about that, Emily. Other questions or comments at the moment? Okay, again, sorry for the confusion on the chat. I'm going to just chalk that one up too. This is a new desktop, so I'm not quite as fluent with working on it. But let's keep on going then. The last problems we got through were admittedly kind of intense problems to get through. But here's a fun part of the course. We have these old derivatives like we mentioned before. Let me make this one a little bit easier to read. Actually, let's just make these bigger. From the prior sections, we know that if y equals e to the x, then its derivative, y prime, is also e to the x. And that's a fantastic formula. It makes it for the world's best derivative in a certain sense, no change when we differentiate those functions. But now what we wonder is, what if y was equal to 3 to the x? It's pretty close as an exponential function goes because e is approximately 2.71. So if we change the base just by a little bit, the derivative in fact does change a good amount. The base 3 is the b that you're seeing here. So the derivative is going to turn into 3 to the power of x. That part is what we expect, like what we did from over here. But then we have to multiply by the natural log of the base. So natural log b copies in. So it's kind of a wild formula. The book derives this one by using properties of exponential functions, and then the chain rule gets used to come up to this total result. But that's how it's going to be used. And in fact, you could have used it here for y equals e to the x. If you used that formula, you would have said y prime equals e to the x multiplied by the natural logarithm of e. But it just so happens that the natural logarithm of e is exactly 1. So that just turns into e to the x times 1 for an e to the x. And that's why this was such a great formula. It's only because natural log e cancels out. But over here, oh, I made a mistake on that one. So it's supposed to be our helpful example. Natural logarithm of base should have been natural log 3, and this one does not cancel out. So that's how our brand new formula goes. And I'd say a bit of a word of warning on this one is this formula is an easy formula to forget because it doesn't get asked a whole lot in the homework questions. And so when it does come up, it almost feels like a surprise every single time. So let's make a big deal out of that. This is an easy one to forget. So if you're ever dealing with an exponential function and the problem just doesn't seem to be working out right, it's probably because we forgot the natural log 3 over here. We weren't using the full formula for a different base. So example 3 is going to work with these ideas, but really we're doing 3 problems at once because it's good to see the difference between all of these 3 different functions. So let's start separating these out. Y equals x cubed, we'll handle that one first. Y equals, oh, I shouldn't have done that one. 3 to the power of x, I guess we've already differentiated that. Let's make a really quick change so I didn't just steal a problem out of nowhere. Let's say that's one base 5. Putting that in red because we made a change right after the notes went live, but that'll make the function seem a little bit more fresh. Sorry about stealing that problem. So that one's 5 to the power of x. And this next one is a base 9 exponential. But the challenge on this one is the power is 3 minus 5x squared. So this one is a chain rule process. This one is an ordinary exponential, but the base is 5 to make it challenging. And the reason we put this one here is, well, the moment we say a formula like this one, it makes this derivative suddenly a lot more tricky. Over here, because x is the base, this is a power function. That's a really super important distinction. If you have your x as the base, it's not an exponent. It being a power function means we differentiate that thing using the power rule. And we just simply say y prime is 3x squared. If we come over here, that process does not work. When we differentiate 5 to the power of x does not come down, and the new exponent is not x minus 1. The reason for that is, here, this time, x is an exponent, not a base, and that means this is an exponential function. Because it's an exponential function, we have to use this formula right here. We're using this formula where b is 5. Once we see that distinction, the derivative is in part, but again, you can imagine how this is a pretty difficult derivative to think about. If it's a power that's a constant, you're using the power function, but the power varies, the derivative on this one is y prime is 5 to the power of x. That's this part of the formula. Then we multiply by the natural log of 5 in this problem. So that's a brand new differentiation formula. Any questions at all, folks, with how we did this example here? Okay, now we're going to do a chain rule problem very next. I would say this is a pretty tricky chain rule. The first thing we want to identify that's going to help us out a huge amount is deciding which function is the actual inner function. Anyone see which function is inner on this one? Turns out it's not the 9. It turns out the 9 is going to be the outer function. Again, that's what makes this one pretty confusing in my opinion. So the function that's inner, whenever it's an exponential function, is the thing that's in the exponent position. So this right here, all of it, the 3 minus 5x squared, that is the inner function. So we'll label it S2, meaning we'll have to handle that one secondly. Again, that's a little bit weird, but the reason it's an inner function is when it's an exponential function like b to the x, and you put something other than an x right here, that becomes the brand new inner function. And the other thing that makes it pretty hard is you might notice that there was a huge pattern like we've been saying before. So let's scroll up here to see some simpler problems. It's often the case that the inner function is this one, and the outer function is the power 103. So same on this one, outer function is the power negative 1/5. The inner function is the thing that's kind of like on the bottom. So what changed? The big change this time was the base has nothing to do with x at all. It's a constant. And the thing that's up here, the exponent, that's the thing that's actually changing, not the thing in the bottom. So we have an inner function, it's the whole exponent right here. And the outer function, which we handle here, is that one. Outer, it's handy to write it as 9 to the power of x just to be specific. That's what that function is as an outer function. So like before, let's differentiate this carefully. Oh, I think I missed a chat. Sorry about that. So Dennis says the inner function is what is happening to x first. The outer function is what modifies x after that. Yeah, I'd say that's really well said, Dana. Another way to think about it is kind of like order of operations. If you plugged in a specific number for x, like maybe 2, the inner function is the things you would have to do first by order of operations. By order of operations, you have to square it, multiply it by 5, take 3 minus that result. Because all of that happens first, that's another reason that's all the inner function. Then after you plug in a number like 2 and calculate all that, then you do 9 to that power, and that's what makes it the outer function, the thing we do last. Well, other questions so far, folks, with the chain rule analysis on that one? Okay, I think on the WebAssign homework, I have a couple questions where it's something like this, a chain rule involving an exponential function. And again, they are very tricky. So this is a good place in the notes to come back to if you feel like you need a really quick refresher. And standard offer all the time, I mention this a lot. If you're dealing with a chain rule section and the problems just seem extra weird, don't hesitate to click on the Ask My Teacher button. I'm always happy to help out with that kind of stuff. But let's color code this like we've had before. The outer function, we've been color coding in blue, and the inner function, we've been color coding in green for these entire notes, except maybe the very first problem. So now if we're going to write out this chain rule, we do the derivative of the outer function first. So this is going to turn into y prime equals, let's write this out carefully. If you differentiate a 9 to the x exponential function, you're doing this kind of process. It starts off as 9, well, it says x there, but our inner function is not just an x. So I'm going to put a big parentheses right here just to say what goes inside. Next, from over here on the function, you multiply by the natural log of 9. And then finally, because it's a chain rule, we say times. Here's the part where we are multiplying by a derivative. Then at this stage, we have our setup with 2 placeholders. The inner function will go inside both of them. 3 minus 5x squared. And 3 minus 5x squared again down here, where it's being differentiated. Some people might like to keep their parentheses right where their 9 is. That's a total stylistic choice. Just it depends on how you like to format your answer. I'm happy with both. Usually I would drop the parentheses on the next step. The whole reason there's parentheses here in the first place is, again, just to organize where things are going in the chain rule. So we're just about there, folks. We just need to finalize that derivative. So copying so far, we have the derivative is y prime equal to 9 to the power of 3 minus 5x squared, multiplying the natural logarithm of 9, and then finally, multiplied by this derivative. It's going to be a 0 to start. 2 comes down to give us a negative 10x. Notice here, the parentheses are absolutely required because if I forgot my parentheses, I wrote it this way. It looks like we're saying some function over here minus another function, but we really intend to say we're multiplying by that other function. So careful with those parentheses. It sometimes can make us lose the question when we're on the right track. An additional thing you could do for extra protection is you could just write this as y prime equals negative 10x, natural log 9 times the exponential function, 9 to the power 3 minus 5. Control Z doesn't really work on this machine. When I hit Control Z, it deletes things in an odd order. That's really weird. 9 to the power of 3 minus 5x squared. So that's how I would probably format my answer to avoid any issues of accidentally saying you're subtracting when you mean to truly multiply, which is better conveyed here, I'd say. Well, we did it, folks. That's the conclusion of example 3. With what we have going forward is, looks like a tangent line equation. Those are always good to add to the notes because it's scattered throughout the chapters, so we'll practice them here and there. Then after that, we'll be doing the application, looking at this situation here. Looks like speed of blood depending on how much the vein has been contracted or dilated. I'd say doing this one right here, finding the tangent line equation, if we really rush through it, we can make that happen, but that's never very satisfying. I don't know if we learn very well when people are racing through the problems. So this is probably a good stopping point for us today, right here. We'll come back on Monday's class next time and finish off these notes. Any questions or comments then, folks, whatsoever? Okay, and maybe another thing to mention, with where we're at so far in the schedule, when we come back next week, we still have to have an ordinary class on Monday, but it's a class right before the exam 2, which is Wednesday, a week away from today. So on Monday the 14th, if you have questions that you'd like to discuss relative to exam 2, don't hesitate to bring to the class. I'll be happy to start out class on Monday, taking whatever questions folks have about the exam. After we run out of questions, then we'll go back to the chain rule section and work from there. So that's our plan so far. And this is where we'll end the notes for the day today. Well, have a great afternoon, folks. Oh, and a great weekend. I guess we'll see each other next week. Thanks, folks. Yep, I'll have office hours 3:30 again today. I think I have another one of those interruptions, but it's going to be, I think, in 1 or 2 weeks on a Wednesday. I'll give everyone a heads up if that happens again coming up here.